I request our academic please remove the slide and give assist to Dr. Kani Mohammed so that he can start the presentation.
Yes, sir. He can share his presentation. Mohammed, sir, please share.
Yes, please. Can you see the slides?
Yes, yes.
Okay. Can I start?
Yes, please. Clear.
Okay. So, good afternoon, everyone. I welcome you all to this faculty development program on quantum sensing. Myself, Kani Mohammed from University of Hyderabad. So, today's lecture, this is the outline of today's lecture. So, although you might have heard lots about quantum sensing, I will briefly introduce what is quantum sensing and what are all the advantages of quantum sensing and what are all the resources that has been used and how they are being exploited to enhance the sensitivity of the instrument. Okay. So I will mainly focus on two scheme. One is based on optical interferometry, where it uses laser light and its interference to detect physical quantities. One of the famous example that I can give you is the gravitational wave observatory, LIGO, where it uses laser interference to detect the gravitational waves. And then I will talk about quantum enhancement in the laser interferometric gravitational observatory. And I will slightly discuss about optical gyroscope, which also involves laser interference to detect the rotation of an object. And another topic that I am going to talk about is atom optics and atomic interferometry. This is similar to optical interferometry, but instead of using light wave, here we use atomic matter wave to detect the physical parameters with an enhanced quantum sensitivity. So this basically involves laser cooling and controlling or manipulating the atomic beams like trapping, reflection, beam splitter that we use by using a light as a source. And this can be used for sensing applications such as quantum gravity or atomic magnetometry, atomic gyroscope, something like that. And then finally, I will conclude about quantum enhancement strategies that can be exploited to enhance the sensitivity of the quantum measurement. So I will briefly discuss what is quantum sensing. Okay. So it's a technology that uses the principle of quantum mechanics to measure physical quantities with extremely high precision. So this basically involves a quantum system. The system can be a quantum system that follows quantum principles. It can be atoms, ions, electrons, photons, phonons, or like solid state quantum systems such as superconducting circuits, nitrogen vacancy centers, quantum dots, and anything that follows quantum principles. And this also involves engineered quantum states such as a quantum superposition state or quantum entanglement. So this involves basically quantum superposition. This may be within the system or it may be between two different systems, like an entanglement. And these are basically the quantum coherence. And this quantum coherence is extremely sensitive to external parameters. So any measurement these sensitivities can allows us to measure the physical parameters such as distance, displacement, velocity, acceleration, force, time or frequency, rotation, mass, charge, fields, electric field or magnetic field, temperature. That there are plenty of things that we can measure it if that this quantum coherence is affected by one of these. So the measurement will lead to measure the physical properties with an enhanced sensitivity because these are highly sensitive to these physical parameters. So now I will talk about the today's topic, which is about quantum sensing based on optical interferometry. So this uses laser light and its interference to detect some changes, physical parameters. So one famous example for laser interferometric quantum sensing is LIGO. So this is a laser interferometric meter gravitational wave observatory, which uses laser light and its interference to detect a tiny changes in the space-time or the stretching and squeezing of the space-time caused by gravitational waves. So whenever we talk about a quantum sensing technique, the first thing we should ask about is what is the sensitivity of the instrument that we are going to use. So here we have to ask what level of accuracy we can achieve in detecting the tiny ripples of the space-times or the stretching and squeezing of the space-times by using this interferometric meter setup. So LIGO is basically a Michelson interferometer, but it's a very huge interferometer, but it is slightly a modified version of Michelson interferometer that we will see in the future slides. So this is a 4-kilometer long arms, and then the interference is being detected at the detector. So any change in the length, the arm length, is going to create a phase difference or the path difference, and that path difference will affect the intensity of the interference pattern that is received by the detector. So this is what the LIGO detects, the change in the intensity resulting from the interference pattern, and its change due to the change in the arm length by the gravitational wave. So let's try to understand what is the sensitivity that we can by using this Michelson interferometer. Okay. So LIGO basically uses laser interferometer to detect the tiny ripples of space-time. So it is the laser that is being used. So we need to understand the nature of laser light from its fundamental perspective in order to understand the sensitivity of the LIGO instrument. Okay. So what is a laser? So it's a highly coherent monochromatic electromagnetic radiation. That's all we know. But we need to understand the laser light, from more fundamental perspective. So from quantum mechanics. So according to quantum mechanics, the electromagnetic fields are quantized into different eigenstates. Okay. So according to quantum mechanics, laser light is a special kind of light, a special superposition state of light, which involves superposition of all the eigenstates. This is called as coherent state. So according to quantum mechanics, laser light is nothing but a superposition state following a Poissonian distribution, and this is named as a coherent state of a single mode radiation. So this is a classical dynamics of the electric field of the electromagnetic wave. But if you want to understand the physical significance of this coherent state, we have to plot the probability density for the electric field as a function of time. So this looks very similar to the classical description of the electromagnetic field, the coherent light. But it looks little bit fuzzy because of the inherent quantum uncertainty that it has. So laser light, from the fundamental point of view, it is the coherent state. So we need to understand the coherent state to estimate the sensitivity of this LIGO instrument detector. So let's review the things on coherent state. So it's a quantum state of light that mostly resembles classical laser light. And this is a minimal uncertainty state. It's a quantum state with a minimal uncertainty in both electric as well as in magnetic field. So this minimal uncertainty doesn't mean that zero. There is still a quantum fluctuations or quantum noise, but it is as small as it is allowed by the Heisenberg uncertainty principle. So there are different definitions one can give for the coherent state. One is it's a special superposition of eigenstate with a Poissonian distribution. It's also an eigenstate of the photon annihilation operator, which has an uncertainty which is same as the uncertainty of the ground state wave function. So, but it is displaced by an amount of alpha. So we can also give another definition that it's a displaced vacuum state, and where D is the displacement operator, which displaces the ground state wave function by an amount of alpha, the phase space. So these are certain definitions for the coherent state. So let's try to understand the noise which are inherent to the coherent state, laser light. So let's start from the basic definitions. The simplest is the definition of coherent state, which is nothing but the eigenstate of the annihilation operator. Okay. But we are more interested in understanding the electric and magnetic fields of the laser light, the electromagnetic waves of the coherent state. So the fields are now represented as field operators, where A and A dagger are the annihilation and creation operator for the photons, and here E naught is this value. Similarly, P naught has this value, and these are nothing but the vacuum field amplitude. This is the vacuum electric field amplitude, and this is vacuum magnetic field amplitude. So this is also called as 0-point fluctuations, which corresponds to the ground state of the electromagnetic field. But the coherent state is not the eigenstate of either E or P. So we don't have a specific value for electric and magnetic field. Rather, it's an eigenstate of the annihilation operator. So we cannot talk about a specific value for the electric field and magnetic field. So what we can talk about is the mean value for the electromagnetic field. So it's very simple to compute what are all the main values for the electric and magnetic field, as the coherent state is nothing but the eigenstate of the annihilation operator. And if we compute the mean value for the electric field corresponding to this coherent state, one get the mean value is E naught into alpha plus alpha star divided by 2, or E naught real part of the alpha. It's nothing but the amplitude. And similarly, the mean value for the magnetic field, one can get it's B naught, it is B naught imaginary part of alpha. So we can try to represent this phase space. So how does it look? It's just a point on the space which is displaced by an amount mod alpha, or as a vector it is displaced by an amount of alpha in the space of electric and magnetic field. So electric and magnetic field are the two conjugate pairs that represents the space similar to the position and momentum for the mechanical systems. But this is for the photons. Okay. And this theta represents the phase of the electromagnetic field. So if we have an amplitude of alpha, so this is the electric field and this is the magnetic field, and the relative phase is theta, which is nothing but the argument of between the electric and magnetic field. And another important quantity that we can compute is the mean photon number, which is the photon number operator is nothing but A dagger A. And for this coherent state, we compute the mean photon number. This is nothing but mod alpha square. So the mean photon number is nothing but mod alpha square. So this displacement is nothing but the square root of the mean photon number. We can also write alpha in terms of mean photon number. But these are just the mean values. But we are trying to estimate the noise or the uncertainty in our measurement. So we need to estimate the variance or the fluctuations or the uncertainty in the electric and magnetic fields. That's what we are finally going to measure it. So let us look at the variance for electric field and magnetic field. So this is the mean value for E squared operator. The mean value for P squared operator we can compute. And as this alpha is an eigenstate of the annihilation operator, this is very simple, and we have used the commutation relation A comma A dagger is equal to 1. And this is the mean value for E square, and this is the mean value for B square, where E and B are given here. Now we can compute the variance in the electric and magnetic field components, which is nothing but the square root of E squared operator, the mean E squared operator, minus mean E square operator. So this we have computed the previous section, and now here we have computed the electric and magnetic field square operator, the mean square operator. So now this turns out to be the variance in the electric field turns out to be E naught by 2. The variance in the magnetic field turns out to be E naught by 2. So this is nothing but the variance for the ground state or the vacuum state of the electromagnetic field. So we say coherent state is a minimal uncertainty state because the variance is minimalized to the uncertainty that the ground state has. So let's try to represent this also the phase diagram. So the dot represents the mean value for the electric and magnetic field, and this circle represents the uncertainty along x and y. In any direction, if you look at, the uncertainty is same as 1 by 2. Here we have written in the unit of E naught and V naught. So here I just talk about 1 by 2 without it's a unitless number in this unit. So this is the uncertainty of the electric and magnetic field. But LIGO is trying to detect the path length difference that is giving rise to a phase difference in the two interfering beams. Okay. So this is the phase of the electromagnetic field, and this is the uncertainty, the phase that the field has. So this is the minimum uncertainty or the minimum precision that we can measure it. We cannot go anything beyond that. So let's try to estimate what this minimum value of phase difference, the phase. So what is the variance in the phase? It's very simple, just using r d theta equal to dx. So now we can compute what the uncertainty or the variance in the phase, which is nothing but delta x divided by mod alpha is the length of this vector. So delta x is the variance of the field perpendicular along this direction, perpendicular to this direction, which is nothing but 1 by 2 because it's just a circle. So the uncertainty is same in all directions. Similarly, mod alpha is nothing but square root of m bar. So the minimum phase that we can measure by using a Michelson interferometer is nothing but 1 over 2 square root of mean photon number. So the variance can be enhanced. Sorry, this uncertainty or the sensitivity, the minimum value of the variance, the sensitivity can be enhanced if we increase the mean photon number or if we increase the amplitude of the laser light. For example, if we increase the laser light amplitude, this is the amplitude, this variance is further reduced. So we could enhance the measurement sensitivity on the phase difference just by increasing the amplitude of the laser light or increasing the power or the intensity of the laser light. So this is the phase difference, that minimum phase difference that one can estimate or measure it from an interferometer technique. But what actually we want to measure is the path length difference that is caused by the gravitational wave passing through the interferometer. The differential path length between the two arms of the interfering beams. So let's estimate what is the minimum displacement or the differential path length that we can estimate by using this interferometer. So the phase is nothing but, just consider the light is traveling a distance of L, having a wave vector k, which is nothing but 2 pi by lambda. So the phase it is going to accumulate is KL. It is the phase. But what is the minimum phase that we can detect is del theta. Then what is from that we can estimate what is the minimum displacement or the differential length that we can detect from this interferometer. So this turns out to be delta theta by k. So we have already estimated what delta theta is, that is 1 over 2 square root of n bar, and k is nothing but 2 pi by lambda. So the minimum displacement sensitivity or the minimum displacement that we can detect is lambda divided by 4 pi square root of n bar. But this is the sensitivity of the instrument when we talk about the displacement sensitivity. But people are more interested in measuring the strain, gravitational strain. That is nothing but gravitational strain. That is nothing but the change in the length over the length L. Okay. So per unit length, actually it is the minimum, the displacement caused by the gravitational wave per unit length. That's what we call it as gravitational strain. The gravitational strain sensitivity can be defined as delta L by L. So this strain sensitivity is lambda divided by 4 pi L to square root of n bar. This is the sensitivity of the LIGO instrument if we consider the noise only from the laser. Okay. So how we can enhance the sensitivity? There are just 3 parameters: lambda, length, as well as the power or the mean photon number of the laser. So lambda, we don't have laser light in all the frequencies. So we have to generate a laser which is highly coherent, which has very minimal fluctuation in its amplitude, phase, as well as its frequency. So we don't have much flexibility on choosing the lambda. We have to choose a best laser source that can generate a highly coherent monochromatic laser light. Okay. So people use, so LIGO actually uses laser wavelength which is of 1064 nanometer, which is okay. And another way that we can enhance the sensitivity is by increasing the arm length. So already LIGO, that's why LIGO uses a 4-kilometer long optical length in order to improve the sensitivity of the strain. But we can further increase, if we further increase the length, we can further increase the sensitivity. So there is a proposal for laser interferometers space antenna. This is a space-based laser interferometry gravitational observatory. So instead of this is a ground-based LIGO, this is a space-based LIGO. So here LIGO uses 4-kilometer arm length, but in space they have proposed using 2.5 into 10 to the power 6 kilometer, a million kilometer length, in order to enhance the sensitivity of the light detection, laser, the gravitational wave detection. So another way we can enhance the sensitivity of the LIGO is by increasing the intensity or the power or the photon numbers of the laser that we are using. So what actually LIGO uses is a wavelength at 1.064 micrometer with a power 20 watt. So even people talk about petawatt lasers, and there are high power lasers which are available. Those are not continuous wave lasers. Those are pulse lasers. But what we have to use is a continuous wave high power laser. So that is very difficult to achieve when we talk about a single monochromatic light. If you want to use a pulse laser, we can have a high power. We can generate a very high power pulse, but that is not useful for gravitational wave detection. We need to have a continuous wave which is highly coherent, a single frequency with a minimum fluctuation in its amplitude, phase, as well as frequency. So what we could have is roughly a few tens of watt that one can generate. But if we can enhance this, improve this laser power, then we can enhance the strain sensitivity, gravitational wave strain sensitivity. So here we use arm length, which is of 4-kilometer length, and both of them are at having same. Initially, they kept at same distance. So the light which is coming this direction have destructive interference. So there won't be any light coming. If there is no gravitational wave, there won't be any light coming in this arm. So all the light which will be reflected back on this, the constructive interference happens on this arm. So the light will actually emerge from that directions when there is no gravitational. So whatever light we are sending it inside the interferometer is been lost. It's been lost in this direction. So one way to increase the intensity is by placing a mirror. This is called a recycling mirror. What it does is this makes a destructive interference for this transmission and constructive interference for reflection. So almost all the light is being reflected back. So the light goes back and forth. Finally, we can achieve a kilowatt power within this interferometer. So this mirror works based on interference principle, not a simple mirror that reflects on only one direction. This actually works on the principle of interference, where the transmissions have a destructive interference and the reflections are having a constructive interference. So whatever the light we are sending is being confined. So the light is getting reflected back and forth. That try to enhance the power of the laser within the interferometer to few kilowatt. So we just started with tens of watt that can be increased to kilowatt power just by using a recycling. But they further want to increase this power. So what they use is not a simple Michelson interferometer, but they use Fabry-Farad cavity within the two arms. So this is the modified version of the Michelson interferometer that they use to detect gravitational wave. These are high quality mirrors, Fabry-Farad mirrors, and now on both the arms, the light is being further confined within this cavity due to back and forth reflections, and this enhances the power to thousands of kilowatts. So initially they start with 20 watt, they can increase into kilowatt by using a recycling mirror, and further putting a Fabry-Forward cavity within the Michelson interferometer arms, the power can be enhanced to thousands of kilowatt, almost 6 order enhancement that will give an enhanced sensitivity. So let's try now. This is not a simple Michelson interferometer. Now we placed a cavity. So now the sensitivity is going to get altered because of this cavity that itself has some resonance frequency. So now the sensitivity becomes, the displacement sensitivity becomes frequency dependent. So in order to see the displacement sensitivity, we have to compute the power spectrum of the displacement, the noise which is contained in the phase and then to its displacement. So the sensitivity is nothing but square root of this power spectrum, the position displacement power spectrum. So if you don't have Michelson the Fabry-Forward cavity, this number is same as the normal one that we have computed. But once we place the Michelson interferometer, this becomes a frequency dependent. And here I have used power that is of thousands of kilowatt, and this gamma is the loss rate of this cavity. So these mirrors are high quality mirrors, and these are like just hundreds of heads. The loss rate is hundreds of heads. So what the frequency that we use is like 10 to the power 15 heads. If you compare to that number, this is extremely small, and these mirrors are ultra high quality, having ultra high quality factors. So using these numbers, if we estimate the displacement sensitivity, this is what we can achieve, which is of the order of 10 to the power minus 19 or 20, 10 to the power minus 20. And at low frequency, this becomes frequency independent. But at high frequency, this becomes omega squared. It goes like omega squared. So this limits the sensitivity. At high frequency, we are going to lose the sensitivity of the Michelson interferometer, the gravitational wave observatory. But okay. So this is just about the electromagnetic phase noise. But this is not the only noise that is limiting the sensitivity of this interferometric measurement. So there are few other noise that we have to take into account. This is the noise that is coming from the laser, the high power laser that we are using. But there are many other noise that actually worsen this sensitivity. That's going to decrease the sensitivity of the instrument. The first one is the seismic noise. It is the grounds, the vibration or the earthquake, whatever that's happening, that is going to destroy the sensitivity of the interferometer. Okay. So whatever we are trying to estimate this number, which is of the order of 10 to the displacement sensitivity, which is of the order of 10 to the power minus 20. It's extremely high sensitivity. Okay. Even a small land vibration can destroy this sensitivity. Not only the earthquake, even because this is a very high sensitive instrument, even if a truck moves close to the observatory, that can cause a small land vibration that will affect the measurement sensitivity of the observatory. So it is that high sensitive. So we have to exclude the seismic noise or any vibration that's coming from the ground or anything which is moving around the observatory. So what they use is a very good vibrational isolation for all the instrument, all the components that they keep it inside the observatory. So these are like completely isolated like from the ground. It has many mechanical element that damps even a small tiny vibrations well below 10 to the power minus 20 meter per square root of hertz will completely isolated and using some vibrational isolation techniques. And now the mirrors are not touching the ground. It's not, instead, this is actually hanging from the vibrational isolation systems. So all the optical elements that they use are being hung on the vibration isolation systems, which completely eliminates even a tiny seismic vibrations that occurs for many reasons. Okay? So by using this vibrational isolation system, they could completely avoid the seismic noise. So this is one noise that has been perfectly eliminated in LIGO. And the next one we have to talk about is thermal noise. Here LIGO uses wavelength which is 1.064 nanometer. It's a near infrared frequency. So even at room temperature, there is nothing to talk about photon thermal noise, because the photon thermal number, if we look at, it will be like 10 to the power minus 50. So that it's actually in the ground state of the mechanic of the mode, optical mode. So as per laser, considering laser, we no need to worry about the thermal noise. But here, all these elements are hung as a pendulum, and these pendulum are having a mechanical frequency which is of the order of 1 hertz. So this, even the room temperature, is going to give a huge noise. It's going to give huge noise because of this low frequency. So the thermal fluctuation in the mirrors is very huge. Even if there is no gravitational wave, there is always going to be a fluctuation on this mirrors. So that's actually going to give a noise on our measurement. So what they have is 1 hertz, but how they can reduce the noise from the mirror is by hanging these mirrors with a support that provides very high quality mechanical oscillation. Okay? So the quality factor of the mechanical oscillations that if you look at for LIGO, which is of the order of 10 to the power 7, it's extremely high. So the tiny vibrations that actually survives for a very long time. And in order to understand the noise, we have to estimate the noise spectral density, the fluctuation density and the displacement. This is just for a mechanical oscillator, which is at a temperature T. If you look at, this is the power spectral density and the displacement. And displacement sensitivity that can be estimated, that is nothing but square root of Sxx. And this omega naught is the frequency of the mirror, and Q is the quality factor. So having high Q, we can actually reduce this number, and similarly having high mass, we can reduce this number. That's why they use, these are not a tiny mirror. They use like a 40 kilogram, a huge, massive mirror, in order to suppress this noise that is coming from the thermal mechanical fluctuations. So having high mass and high quality factor, this is the frequency dependent noise that is coming from the thermal motion of the mechanical element. So this is the resonance frequency. So if we work at resonance frequency, this noise is very huge. Even a tiny fluctuations, this will actually pick up, and the noise will be huge at this frequency. But if we go far from the mechanical frequency, the resonance frequency, this has been drastically reduced to the level like 10 to the power minus 20. Okay? So the three noises that we have is, one is the laser noise, the phase noise that is in the laser. Another one is seismic noise that has been reduced by using a isolation, vibrational isolation technique. And another noise, important noise, is the thermal fluctuations on the mirror at the room temperatures. But cooling this we can reduce, but these are 40 kilogram mirrors. So cooling this to ground state is not, and that also at 1 hertz frequency. So cooling is really not possible. So we have to work at room temperature, but we can enhance it just by increasing this and increasing the quality factor. So now let's try to estimate the total sensitivity, the displacement sensitivity that one can get from this interferometer. So this is the total power spectrum. The first one is the thermal noise, which is coming from the fluctuations of the mirror. And the second one is the phase fluctuations that are in the laser. And then this is the total power spectral density and the total power noise in the displacement that can be computed just by taking the square root of S6. So this is the thermal noise. Here I have plotted. This is the thermal noise as a function of frequency, and this is the thermal noise in the mechanical element, and this is the phase noise in the laser, the high power laser, and overall sensitivity is plotted on the line plotted. So the minimum sensitivity that we can achieve is in the order of 10 to the power minus 19. For thousands of kilowatt power with an ultra high Fabry-Farad gravity with a mechanical element having a quality factor of 10 to the power 7, having the mass of 40 kilogram, we can achieve a sensitivity on the differential path length difference, which is of the order of 10 to the power minus 19. And we use 4 kilometer ohms. So in terms of strain sensitivity, this is further reduced almost 4 order. So it is like 10 to the power minus 21, 23 is the sensitivity for the strain that can be the strain sensitivity of the strain that gives this LIGO observatory. So this is an extremely good quantum sensor having a sensitivity on the strain is which is 10 to the power minus 22 per square root of hertz. That allows us to detect a tiny change in the strain, which is of the order of 10 to the power minus 20 per meter. 1 meter is the space is extended or compressed by an amount of 10 to the power minus 21 or 22. This instrument can detect that small change. Okay. So this is the first generation LIGO, the laser interferometric gravitational observatory, with a strain sensitivity of 10 to the power minus 22. But we can further increase this sensitivity if we actually use some quantum enhancement strategy. So the first generation LIGO just uses coherent state, a kind of classical light. But we can further enhance the sensitivity if we use skews light. So let's understand what is a skews light. So this is a coherent state having an uncertainty of 1 by 2 in its quadrature. So this gives the phase uncertainty, which is of 1 by 2 square root of mean photon number. But if we can reduce the uncertainty in the angular direction, something like this, then we can improve the sensitivity of the measurement. Okay. So this is what called skewing, or the light which is generated by skewing the quadrature. Any quadrature is called skews light. So here we are mostly interested in skewing in the angular direction. So that's what is going to reduce the uncertainty in the phase noise. Okay. So this is called phase skewing. And we can also have amplitude skewing, but that will enhance this delta theta, the uncertainty in the phase. So how one can generate this, how one can describe this skews light is something called skewing operator. So skewing operator and vacuum state is actually going to skew one of the quadrature. So, but what is the actual experimental principle that one can use it to generate skews light? So that is by using a degenerate parametric amplifier. This is nothing but the cavity system, but it involves a nonlinear crystal, a second order nonlinear crystal. So what it happens, so this is the Hamiltonian of this system where A and B are the two different optical modes. What it happens if we send an optical mode of B, one photon of B gets annihilates and creates two photons in the mode A. And those two are the same frequency. That's why we call it as degenerate parametric amplifier. And it is vice versa. So one photon will be created in B mode will be created when two photons in the mode A gets annihilated. So this is the basic principle of parametric amplifier. And now we use a coherent light. Let's try to inject a coherent light, a high intensity laser light for the mode B. So now this can be reduced as it is a coherent state with a very huge amplitude. We can treat it like a classical light. And now the interaction Hamiltonian is nothing but A squared alpha star plus A dagger squared alpha. So what, just by injecting a high intense coherent light of mode B at frequency omega, we can generate a light at frequency 2 omega, which is going to be a skews light. So this is a coherent light, but once if we drive this parametric amplifier at this frequency, we can generate a skews light at frequency 2 omega, and this is about phase skewing, where the phase is being squeezed, and this is generating an amplitude skewing. We can actually have a space, we can generate a phase skews light or amplitude skews light depending on this complex number. If it is a real number, we can generate a phase skews light. If it is on a complex number, we can generate a amplitude skews light, like imaginary number, or if it is a general complex number, we can squeeze it in any linear combination of both amplitude and phase. So just by playing with this alpha, the complex number, we can generate a phase skews light or amplitude skews light or a general skews light. But what we are mostly interested in here is generating a phase fused laser light, where the phase is being skewed. So now instead of using a coherent light, if we use a skews light, so the skews light actually described as same as like will have an uncertainty same as a coherent state, but 1 by 2 e to the power minus epsilon, where this epsilon is called skewing parameter. The amount of skewing that is experienced in a particular direction. Here it is on the angular direction. So this is the uncertainty that one can have when we are having a phase fused light. Okay. So now if we use a phase fused light, this is the sensitivity on the displacement that one can achieve in LIGO. So this, when epsilon is 0, when there is no skewing, this is the total uncertainty and this is the minimum uncertainty that we can achieve. But if we improve the skewing to epsilon equal to 1, we can improve the sensitivity, and if we improve the skewing, we can further improve. So the sensitivity is not limited here by any principle. just by increasing the squeezing, we can enhance the sensitivity. But there are certain experimental constraints on how much we can squeeze the light in, and what is the minimum sensitivity that we can achieve from light. So this is all about detecting gravitational wave by using optical interferometer and enhancing the sensitivity by using quantum squeezing. And I will talk about another similar interferometer technique, that is optical gyroscope. This is another quantum sensing technique which relies on same and similar principle of optical interference. So here the light is being split into a simple coherent light is being split into two beams which are traveling in a closed circular loop. Okay. So, and the entire setup, consider the entire setup is rotating. So the optical gyroscope is nothing but detecting the rotational. We are trying to, it's an instrument trying to detect the rotational speed or the frequency of the complete setup. So the basic mechanism is just by splitting the light into two, and they are actually traveling in an opposite circular path. If there is no rotation, both the light and will get recombined here. Okay? And both the light path will take the same time, and there won't be any phase difference between these two if there is no rotation. So finally, zero phase difference between the two light. But if the entire instrument it rotates, the light which is traveling along the direction of the rotation needs to travel extra length, whereas the light which is traveling opposite to the direction of the rotation will travel less length when it gets recombined. So this is actually going to create the path length difference or the phase difference, and that is going to affect the interference intensity that finally we are going to observe here. Okay. So this phase difference actually depends on the rotational speed of this instrument as well as the area of this setup and the wavelength. So this is called Sagnac effect. So the rotational speed is going to affect the phase difference between the two light which are traveling in the opposite circular path. It not necessarily to be a circular, but any closed loop. So the area comes a general, whatever may be a shape. It may be a triangular or like a Alexander interferometer. So this is the area of the complete loop. So just by measuring the phase difference or the intensity of the interference speed, we can estimate the rotational speed, which is nothing but lambda c divided by 8 by a into pi. So this phi, now we can ask about what is the minimum or what is the sensitivity that we can achieve while measuring the rotational speed of this instrument. So this is nothing but related to delta phi. It is the minimum, the sensitivity that we can achieve on the phase estimation of this laser. So that is inversely proportional to the square root of delta. Okay. So here we can increase the sensitivity by increasing the area, but we cannot have something like a huge LIGO, like 4 km arm. So we do have a constraint on this area. We cannot increase it to too much if you want to have a compact gyroscope, but we can increase the number, photon number or the intensity to increase this rotational speed. And in a normal setup, lab setup itself, we can have something like 10 to the power minus 10 radian per square root of meters. Can be easily achieved when we use this interferometric technique to measure the rotational speed of the instrument. So this is all about optical interference technique that can be used for quantum sensing. So now I will talk about atomic interferometric technique. So this involves atom optics. So in optical interferometry, we use light and it's the laser light and its interference to measure the physical parameter. But here we are going to use atoms, more specifically matter wave and the interference of the matter wave in order to estimate certain physical parameters that affects the interference pattern. So it basically comes from atom optics, not the normal laser or light optics. So this uses matter wave instead of light wave. So in optics, we have many optical elements. Those are matters like mirror, lens, beam splitter, polarizer. These are the optical elements that we actually use in order to redirect, recombine, or split, and in order to make an interferometer, optical interferometer, or in order to manipulate the light and its directions, it's to recombine everything. So these are the optical elements made of matter that are being used in optics to make an optical interferometer. But here we are going to use matter wave. And here we can manipulate the matter wave by using light. So this becomes one-to-one correspondence for optics to matter wave. It's very simple idea that we can take, but we are using matter wave and we are using light to manipulate the matter. So the main important thing is cooling the atoms. Because if you want to observe matter wave, the first thing we have to do is we have to cool the atoms. Once we have cooled the atom, we can observe the matter wave, and we can also trap the atom. We can deflect the wave, matter wave, and we can split, we can recombine, and we can make an interferometer, but this is for matter wave instead of light. And similar to the optical interferometry, this interferometry is also very useful to make something like atomic gravimetry, atomic gyroscope, atomic clock, and there are many things that can be exploited by using atomic interferometry. So let's start from matter wave. So this is a de Broglie wave of matter. But if we look at normal room temperature, the atoms are moving very fast, which is almost like 500 meter per second, roughly. So if we estimate the de Broglie wavelength of atoms at room temperature, the air molecules or the atoms, it comes out like 10 to the power minus 11 meter. But the atom size itself is roughly of angstroms. So this de Broglie wavelength is much smaller than the typical size of the atom. So we are not going to see any quantum behavior. So at room temperature, this gas, atoms, whatever there, they act like classical particles. They are not following a quantum principles because of this extremely large speed that reduces the de Broglie wavelength of the atoms. So in order to observe quantum phenomena like matter wave or Bose condensations and matter wave interferometry like anything, the first step is to cool the atoms. So if we cool this atom to something like microkelvin temperature, the speed drops dramatically to few centimeter per second, and the de Broglie wavelength becomes few micrometer. So this micrometer is much larger than the typical atomic size, which is of the order of few angstrom. So cooling the atom can actually observe the matter wave, and then we can do matter wave interferometry. So the first step, what we have to do is to cool the atoms below around microkelvin temperature. So the basic idea for cooling is laser cooling. Light. Now the light is being used to cool the atoms, manipulate the atoms, and to create the matter. So consider an atom like a two-level system which is moving with a momentum mv. Under laser light of photon, each photon having a momentum of h cross k is traveling towards the atom. So both of them are moving in the opposite directions. So if the atom absorbs this photon, the energy, the atom goes from the ground state to the excited state. So the energy of h cross omega has been absorbed by the atom. But we also take care of the momentum conservation. So now the atom will gain the momentum of h cross k in the corresponding direction. So because the light is moving in the opposite direction, so if an atom absorbs a photon, the momentum will be reduced by an amount of h cross k. But atom will not stay in the excited state itself. So eventually it will decay and it will radiate spontaneously that absorbed photon, but that direction is random. So on an average, if we look at, this is not going to gain or lose any momentum because of the radiation which are taking place in all the directions. So if a photon gets absorbed by an atom moving towards the laser light, the momentum gets reduced by an amount of h cross k. So if the thing happens multiple times, eventually the momentum of the atom will get reduced and gets cooled to a low temperature. But there is a problem here. So this is not just a laser cooling, something called Doppler cooling. Let's understand the laser cooling in a better sense. So now the atom is moving with certain velocity, certain v. If the atom is not moving, this is the absorption spectrum of the atom. An atom has a resonance frequency omega naught, that is the frequency difference between the ground and excited state. So the maximum amount of absorption happens at this frequency. So if you look at the previous case, if we send a light at this frequency, this atom will absorb more number of photons and eventually it gets cooled down. But because the atom is moving, this atom will see this frequency which is slightly shifted. This is called Doppler frequency shift. Doppler shift in the frequency. So although we send the light which is at frequency omega, but the atom is going to see the light having the frequency which is omega plus kv, where v is the velocity of the light and k is the wave vector of this laser. So if we send a light at this resonance frequency, the atom sees the light which is slightly larger. So here the absorption is actually being very less. So this is not going to give any effectively, it's not going to cool the atom. So what we have to do is to adjust this frequency. So instead of sending the frequency which is at the resonance frequency of the atom, if we send a frequency that is less than the resonance frequency. This is also called red tuned laser. Then the atom will see that this laser is at its resonance frequency. So it's going to absorb effectively and then it gets cooled down. So if we use a red detuned laser, we can effectively cool the atoms which are moving towards the laser light. But what if the atom is moving in the opposite direction? If the atom moves in the opposite direction, so now this is going to see that frequency is like omega minus k. This is further red detuned, and where the absorption is very minimum. So the cooling is not going to effectively the cooling is not going to take place. Okay? So only the atoms which are moving towards the laser light is being cooled by this laser beam. So what we have to use is 6 different beams. If you want to cool the atoms in all the 6 directions, we have to use 6 different beams, and all of them are red detuned to the resonance frequency of the atom. Then we can effectively cool the atom to microkelvin temperature. So there is something fundamental limit. Okay? So finally, what happens here is the photons which are being radiated in a random directions. So now there is even if the atom is being cooled to low temperature, because of this random emission, this is going to experience small kick in the random directions on all directions. So this is actually going to limit this cooling mechanism that is called Doppler cooling. So this the minimum temperature that we can achieve when we use Doppler cooling mechanism to cool the atomic system, which has the line width of gamma. Gamma is the absorption line width. And for a typical atoms like sodium, rubidium, whatever that we use in lab, so we can easily achieve hundreds of microkelvin through Doppler cooling mechanism. So this itself will create a matter wave of wavelength which is of few micrometer. So that is sufficient to observe matter wave and matter wave interferometry and matter wave interferometry based quantum sensing and for more. So this is the basic things that we need to do. Now we have cooled the atom and we have created matter wave like an optical wave. But next thing we have to manipulate or we have to redirect, we have to use like kind of optical element that we use in optics. We have to make some elements for matter waves. But here what nice idea is we are going to use certain going to use laser light itself. Okay? So now we have cooled the atoms by using Doppler cooling mechanisms. But after cooling that, same like optics, we can trap the atoms just by using laser light. We can trap the atoms and we will talk about mirrors, beam splitter in the next step. So the next step is after cooling is about trapping the atom by using laser light. Okay. So now consider a laser beam. The atom is being cooled to very low temperature and now it is being placed in a laser beam. So that is going to, this laser light is going to interact with the atom and this is going to induce dipole moment. The oscillating electric field of the laser light induces the dipole moment. So now this dipole moment interacts with the light field, nothing but the oscillating electromagnetic field. So now the light is going to, this interaction of light and atom is going to exert a force on the atom. A dipole force will be exerted on the atom and this dipole force is proportional to alpha into gradient of the intensity. So alpha is nothing but the polarizability of the atom, and I is the intensity of the laser. Okay. So if we have a uniform, a plane wave kind of laser, we are not going to see any dipole force. This is a dipole force, but what we were talking about when cooling the mechanism, that's a scattering force. So this is a dipole force that is experienced by a dipole in an electromagnetic field. So similarly, we can write the potential, which is nothing but minus alpha I. If I is constant, a plane wave, then there won't be any force and the potential is just a neutral. But just by playing with this profile, intensity profile of the laser beam, we can actually trap the atom. So if we use a focused beam, okay, where the intensity is getting minimum, maximum at its focus, we use a like intensity focus beam, the intensity is actually getting maximum at its focus. Now the potential is going to create kind of this intensity variation is going to create a kind of potential for the dipole, the atoms. And if we cool, already we have cooled the atoms to sufficiently low temperature. So this actually can be trapped. Now the cold atom can be trapped in this optical trap. And the focusing, so the intensity is variation is not just on the one direction. So intensity variation, if you look at in all the three directions, it's actually getting maximized to its center. So even by just by using a single focused laser beam, we can create a 3D trap that actually confines the cold atoms in all three directions. Okay. So we have created a matter waves, and that matter wave is being now trapped inside a trap which is being created by a laser. Okay. So next optical element, this is a kind of like a resonator for optics, and next we can talk about mirrors for atoms. So metals are very good reflectors for light, just consider. But now here we are going to create some kind of optical element to deflect the beam of atoms or the matter waves, just like a mirror that we use in optics, standard optics. Okay. So the principle is very simple. Just consider a cold atoms, which are actually in the ground state, usually which are in the ground state, and which is moving at some momentum p. So in the momentum state, this is in the energy state. The atom which is cooled to the ground, which is in the ground, cold atom which is in the ground state of the energy, which is moving at some momentum p, and which is in the momentum state p. Okay. If we apply a pi pulse, what it actually makes, the atom being the atom which is in the ground state gets excited to the all the atoms which are in the ground states gets to the excited state. So now just by applying a pi pulse, the pi pulse is the duration of the pulse that we are applying to the atom, which makes all the atoms to go to the excited state from the ground state. So now it absorbs, all the atoms absorbs an energy of H cross omega, each photon. Same way, if you look at, it's going to absorb, each atom is going to absorb the momentum of H cross K from each photon. So now the atom initially moving with the momentum P can be deflected in different directions just by using a laser light pulse having a width of pi. So a pi pulse can be used to deflect a light, and which acts like a mirror for optics. Like this acts like a mirror. So next we will talk about beam splitter, atomic beam splitter. So optical beam splitter, we know that's a partially silver mirror that we use it to split laser light into two different directions with equal intensity. Okay. So similarly, we are trying to split the beam of the atoms or matter wave into two coherent parts. Same like beam splitter, which divides light into two different directions with equal intensities. Okay, 50-50% beam splitter. So here also the idea is very simple. Same way, consider the atom which is the ground state and which is moving with the velocity, which is moving with the momentum p. But instead of applying a pi pulse, if we apply a pi by 2 pulse, what it creates is the atom which is in the coherent superposition of ground and excited state. I haven't put the normalization constant, so forget about that. But a pi by 2 pulse creates coherent superposition of atoms. Half the atoms are in the ground state and half the atoms are in the excited state, but it is in a coherent superposition state. Not separately. It's a coherent superposition of atom being in the ground as well as in the excited state. But if you use a pi pulse, all the atoms will go into the excited state. But if you use pi by 2 pulse, half the atoms going into the excited state, and now the atoms are in the superposition of ground and excited state. And now if we look at the momentum basis, now it is in the superposition of P plus P plus H cross K. So now we have created a coherent superposition of beam traveling in two different directions with the momentum P and P plus H cross K. So one part of the light is going as it is, one part of the atomic beam is going as it is, and another part gets deflected and going on the direction P plus H cross K. So using pi by 2 pulse, we can split the atoms in a coherent superposition state with an equal intensity on both the directions. So a pi by 2 pulse acts like a 50-50 beam splitter. But here a pi pulse acts like a mirror. A pi by 2 pulse acts like a 50-50 beam splitter. So these are the main elements that we need to understand. We want to construct a kind of interferometry meter for atomic beam. So this is a simple example for atomic interferometer. This is the famous optical interferometer called Maxwell interferometer, where the light is being sent, and this is a beam splitter mirror which are being used to split the light beam and then change its direction and then finally recombine the light beams and try to detect anything that is giving a change in the phase of this beam that we can detect. And it is similar like the phase uncertainty that already we have estimated for a laser light. So that is inversely proportional to the square root of the mean photon numbers in this laser beam. So this is the basic optical interferometer we use to detect a phase difference caused by any physical parameter in any of these form. So similar thing we can construct for atomic Alexander interferometer. The first thing, we can split the atoms. So first initially prepare the atoms in the ground state and use a pi by 2 pulse. That is going to split beta wave or the atomic beam into two directions without destroying the coherence coefficients, without destroying the coherence between the poles. Okay. So here also the coherence is very important in order to observe the interference pattern. So still they are traveling in different directions, but still the coherent superposition between the two beams are kept as it is. So next thing, we have to use mirrors to change the directions in order to recombine the two beams to observe the interference pattern. So initially we used pi by 2 pulse to split the atomic beam, and then now we can use pi pulse. What this pi pulse does, this inverts the coherence superposition. The 0 becomes 1 and 1 becomes 0. So now this beam is initially gained a momentum of h cross k, and now it is actually losing the momentum h cross k. So now this beam travels as it is, but now this is being excited. So what has been done here is just flipping the excited state atoms to the ground state and ground state atom to the excited states. And that causes deflections on the two poles, both the beams. And finally, we have to recombine. Okay. So again, we use a pi by 2 pulse. That pi by 2 pulse changes the excited state population to the ground state populations. So everything now becomes ground state population. But the final thing will carry certain information about the phase that it occurred while traveling on this path. So finally, if we detect the number of atoms which are in the excited state or number of atoms which are in the ground state, we can estimate the phase that it has occurred while traveling in this path. Here we haven't put any element or anything that actually can introduce an extra phase between the two arms. But if any physical parameter that introduces a phase difference between two paths, that we can estimate. That physical parameter can be estimated just by measuring the phase difference or just by looking the atoms which are in the excited state and the ground state. Same like optical interference technique. So this optical interference technique that you will be in the upcoming lectures, you will be here a lot, but I will just give a small idea about its use in detecting gravitational acceleration, and this is called atomic gravimetry. You can also use it for accelerometer, atomic accelerometer, but this purpose is mainly to detect the gravitational acceleration. See, okay. So just consider a cold atoms, a matter wave, which is initially trapped. We actually cooled the atoms and we trap the atoms in a trap, in an optical dipole trap. Now let's release the trap. So what happens? The cold atom is going to fall down and it is going to experience an acceleration c. Okay. So now we will try to use an interferometry to detect the phase that it is going to occur while accelerating towards the ground. So first we can use a pi by 2 pulse to split the atom into two. One which is traveling as it is, another one which is actually going to get a momentum from upward. The light is being sent from upward, so it is going to gain a momentum of plus h cross k. So it gets deflected the downward direction. So now after a time t, we can send a pi pulse that inverts the population. Now this actually gains a momentum of h cross k, and this is going to gain a momentum of minus h cross k with respect to the previous direction. And finally, in order to recombine everything, after the same time t, we apply another pi by 2 pulse and recombine both and measure the atoms which are in the excited state, the probability of atoms which are being in the excited state as well as the ground state, in order to estimate the phase difference that is caused by the gravitational acceleration. So what is the phase difference in the acceleration, which is nothing but k effective is the effective k of the photon, because it can be of different frequency. So we use an effective k vector. G into t squared is the time of the pulse sequence that we used. So just by measuring the phase difference between the two arms through atomic interferometry technique, we can estimate the acceleration of gravity. It's nothing but the phase difference divided by effective k vector and t squared, that pulse sequence time. But we need to ask, what is the sensitivity that we can achieve when we use this atomic interferometer to detect the gravitational acceleration? Okay. So the uncertainty is mainly in the phase difference. So the same like at optical interferometry, the uncertainty or the variance in the phase is now proportional to the number of atoms which we are using it, this interferometer, instead of the number of photons that has been used in the optical interferometry. So this is the minimum acceleration, gravitational acceleration, that we can detect by using atomic gravimetry. So how can we enhance the sensitivity? These are the parameters: k effective, t squared, and square root of the number of atoms that we are using it here. So k is the wavelength of the light that we are using. But we don't have much control on k, because we have to choose the k vector which is close to the resonance of the atoms. So we don't have much control. It has been already set by the resonance frequency of the atom. So this won't help. And t squared, so if we increase this time, it looks like we can increase the sensitivity of the measurement. But we have to make this measurement before atom decommits. So there is a spontaneous emission rate, the spontaneous emission lifetime, that limits how big the t we can choose. If we choose the time which is larger than the spontaneous emission, this actually won't be any coherence between the two peaks. It will be completely lost. So whatever the measurement that we are doing, we have to do well within the limit of the spontaneous lifetime. So we don't have much control on this t. T is typically like megahertz for the atoms. T is like a microsecond for the atoms. So we have to do everything within the microsecond time scales. So we don't have much control on this. And this is the only parameter that we have in control is the number of atoms, the number of the clouds, the beam of atoms that we are going to use for this interferometry. But when cooling the atoms, we cannot cool huge number of atoms, and we cannot trap that much. Okay? So typically there is a constraint on how many number of atom itself can be cooled and trapped within the optical trap. And if you look at Bose-Einstein condensations, that number is even less than that. Okay? So this number is typically like 10 to the power 6. It's not, we cannot have huge number of atoms. that can be cooled simultaneously and can be trapped in an optical trap, because even a small fluctuations within the atoms will try to kick each and every atoms outside the trap. So we have a limit on the number of atoms that can be cooled and trapped within the optical dipole trap before starting the experiment. So this number is also like limited, like 10 to the power 6 maximum of it. So within the experimental, the lab constraint of k, time, and the number of atoms, one can easily achieve a sensitivity and the acceleration due to gravity is like 10 to the power minus 9 g per square root of x. This is a very, it doesn't look like sensitivity like a LIGO, but this itself is a very good sensitivity. Like G is like 9.8, like 10, but the sensitivity that we are getting is like 10 to the power minus 9 G. Okay. So even a small change in the G, which is in the order of 10 to the power minus 9, can be detected by using atomic interferometry. So anything like groundwater or tidal motion will affect well below this limit. So this accelerometer is very useful for geological applications and things, for estimating, for a real-time applications of doing some other physical measurements. So this is all about the atomic interferometry, and you will hear more about this one in the upcoming lectures. So I will try to conclude my talk. So I have talked about the quantum sensing, just about the introduction, introduce the quantum sensing and quantum advantage. Here the quantum advantage is like coherence is the major resource. People can also use entanglement is another kind of coherence as a resource. But in this interferometric technique, we mainly use the coherence of coherent light and the coherence of atomic beam or the laser beam in order to measure the physical parameter that changes the phase of the light as well as the phase of the matter wave. Okay. And I talked about optical interferometry, a simple Michelson interferometry technique in order to describe the gravitational wave detection and optical gyroscope just by using a classical kind of light, that is a coherent light or the laser light. The enhancement is mainly comes from the intensity of the light to detect the phase difference or the gravitational wave, as well as the size of the interferometer that can use change if you want to increase the sensitivity. And we can further enhance if we skews the light, or if we skews, especially if we skews the phase variance of the light. So there is no limit, there is no fundamental limit on how small we can measure. Everything are limited by the experimental constraints. Okay. So we can further enhance if we use a diffuse light or something, we can further enhance the sensitivity for to any precision. Currently, they are under the experimental constraint that what we have. Similarly, we can use atoms or matter waves to do interference to measure something like acceleration, gravitation, force that actually experienced by the atom that actually causes the phase difference on the matter wave. But here the first step is laser cooling is the very important thing, and then cold atom will be kept in an optical trap, and then we use light like a mirror, beam splitters to construct a kind of interferometry. And finally, we use to estimate the phase difference causing any external physical parameter with a sensitivity that mainly limited by the number of cold atoms that has been made before starting the technique. So I will stop it and let's have a discussion on what I have taught.
Thank you, sir, for your talk. If there is any query from the participants, please post in the chat box or raise your hand so that I can pass it to the speaker. Okay, so I could not see any queries from the participants. Can we simulate anything? Anything sensing? You are, I think, muted, Dr. Kani Mohammed. Please stop sharing, and then I think you just
Hello,
stop
Mohammed sir,
sharing.
you can speak. Now you are unmuted.
Sir,
I think your mic is not working properly. Your headphone is not having an inbuilt mic. So if you are from laptop, you can directly speak without headphone. Maybe the inbuilt mic will work. Previously, the all talk is fine. So your mic is working perfectly when you are going to present something. This is the problem coming here. Because throughout the lecture, your voice is loud and clear, but now we are unable to listen you.
no. No. Maybe in the left panel where this mute is written, just click the arrow and select your microphone.
Yes, it has been.
Yes, yes, perfect, perfect. Now,
Okay, yeah, thank you. Yes.
so the question is, can we simulate anything sensing using open tool at our PCs?
Open Using-
Tool at our personal computers.
Yes, you can simulate everything. Mainly, it actually starts from the basic theory only, and then it's mainly estimating the noise spectral density for different kind of things, whatever. So, like mechanical, what element or optics? What is the power spectral density, the noise spectral density that we have to simulate from the graph?
So next, what are the open source tools?
Open source tools, I don't know, but I actually use Python's Mathematica things to simulate the thing, or like Qt. Sometimes I use it if the numbers Hilbert space is so small, then I can use Qt for things to do simulation, quantum simulations.
Okay. So since there are no other questions, so let us thank speaker Dr. Kani Mohammed for his talk today. So sir, it's wonderful to have you online today and for your talk. So on behalf of participants as well as our personal behalf, I thank you for joining us today and for your talk. So thank you very much, sir. Thank you.